Hello there, and welcome to the Sleepy Thought channel. Tonight we'll be exploring one of humanity's oldest mysteries. Comets are not just shiny objects in the night sky. They are frozen remnants from the very beginning of our solar system. Long before Earth had oceans, comets were already forming in the cold darkness around the young sun. For most of their lives, they remain almost invisible. They wait far beyond the planets, where some light is weak, and time almost feels like it doesn't exist. But then something changes. Gravity shifts their path, the sun begins to warn them, ice turns into gas, and their hidden body begins to shine. What was once a dark hidden world becomes a bright, breathing cloud of dust and vapor. For ancient people, comets could feel like messengers or warnings, but for modern science, they are messengers for another reason. They carry pieces of our lost beginnings and may hold clues about how we got here. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, to one sleepy soul at a time. But for now, all you need to do is settle in. Allow your body to soften. Allow your breathing to slow. And as your mind begins to settle into stillness, join me as we journey through the cosmos together. Let's begin. Comets are ancient leftovers from the birth of our solar system. Long before Earth had oceans, mountains, or a moon, tiny grains of dust and ice were swirling around the newborn sun. Most of that material gathered into planets, but some pieces were left behind in the cold outer reaches. Those frozen remnants became comets. They are not just space rocks, they are time capsules. Inside them are ices, minerals, and carbon-rich compounds that have changed very little since the solar system formed. When scientists study a comet, they are not only studying an object in space, they are sampling the ingredients of our cosmic beginning. A comet may look small from Earth. It occurs a memory older than every living thing, older than every mountain range, and older than the planet beneath your feet. A comet can grow a glowing head larger than Jupiter. The solid heart of a comet may be only a few miles wide, but when it nears the sun, everything changes. Heat begins to loosen frozen gases from the surface, and those gases drag dust outward into space. Around the nucleus, a huge hazy cloud forms. This is called the coma, and it can swell to a truly astonishing size. In some cases, the shining envelope around a comet becomes larger than the biggest planet in our solar system. That means a tiny frozen body can briefly wear an atmosphere wider than Jupiter. The scale feels almost unreal. A dark lump of ancient ice smaller than a city can transform into a vast glowing presence that fills an enormous region of space. Comet tails can stretch for millions of miles through space. A comet's tail is not dragged behind it like smoke behind a train. It is shaped by sunlight and the solar wind, which push dust and charged gas away from the nucleus. As the comet travels inward, material streams outward and can spread across distances that dwarf the planets themselves. Some tails stretch so far that Earth could fit inside their length many times over. Yet the material is incredibly thin, more like a faint veil than a solid trail. From far away, it glows beautifully against the dark. Up close, it would be almost emptiness. That contrast is part of the wonder. A comet can paint a path across space that looks grand and radiant while being made from scattered particles thinner than any cloud on Earth. Every comet tail points away from the sun. It seems natural to imagine a tail trailing behind a comet's motion, but comets follow a stranger rule. The tails are driven by the sun, not by the direction they travel. Radiation pushes dust outward, while the solar wind sweeps charged gas away in a straighter stream. So as a comet rounds the sun and begins moving back into deeper space, its tail can actually point ahead of it. The comet is flying one way, while the tail reaches in another. This simple detail reveals something invisible and powerful. Space is not empty stillness. It is filled with light pressure, magnetic fields, and flowing particles from the sun. A comet makes those hidden forces visible, like a weather vane turning in a cosmic wind. Some comets may carry ingredients linked to life's chemistry. Comets are frozen dark and lifeless, yet their chemistry is surprisingly rich. spacecraft and telescopes have found carbon-bearing molecules in comet material, including compounds related to the chemistry used by living cells. That does not mean comets contain life, but it does mean they carry some of the raw ingredients that life can use. In the young solar system, impacts were far more common than they are today. Comets and similar icy bodies may have delivered water-carbon compounds and other volatile materials to early worlds. Earth was not born finished. It was shaped by bombardment, heat, oceans, and chemistry. Comets may have been part of that story, bringing fragile molecular seeds from the cold outskirts into the warmer inner solar system. Halley's Comet has appeared in the night sky for millennia, long before anyone understood orbit's gravity or the true nature of comets. People were watching this famous visitor cross the sky. Ancient records from several cultures describe bright comet appearances that match its returns. To those observers, it was not a predictable traveler. It was a sudden blazing sign in the heavens, arriving without explanation. Later, astronomers realized that many historical sightings were the same object coming back again and again. That discovery changed comets from omens into worlds with paths. The most remarkable part is the human continuity. People separated by empires, languages, and thousands of years looked up at the same icy body. It has passed over farmers, kings, monks, scientists, and modern cities, linking generations through a visitor. That keeps returning from the dark. A comet once slammed into Jupiter and left Earth-sized scars. In 1994, the broken pieces of shoemaker Levi 9 struck Jupiter one after another. Astronomers watched in amazement as dark marks bloomed across the giant planet's cloud tops. Some of those impact scars were comparable in size to Earth. The event showed in real time that the solar system is still active and sometimes violent. Jupiter's immense gravity had pulled the comet apart before impact, turning it into a chain of fragments. When those pieces hit, they released staggering energy into the atmosphere. For many people, it was the first modern reminder that cosmic collisions are not only ancient history, they can happen while telescopes are watching. Jupiter absorbed the blows, and the marks faded, but the lesson remained vivid. Most comets spend their lives frozen in deep darkness. The spectacular part of a comet's life is usually brief. For most of its existence, it is far from the sun, cold, dim, and nearly invisible out there. Ices remain locked solid, and the comet does not shine with a tail or glowing cloud. It simply follows its long path through darkness, sometimes for centuries, sometimes for thousands of years, and sometimes far longer. Then a small change in orbit can bring it inward. Sunlight returns, frozen gas is awakened, and the hidden body becomes a luminous visitor. This rhythm makes comets feel almost like sleepers. They spend ages in silence, preserving old material in the cold before one close approach turns them briefly into wonders seen across the sky. A comet is darker than coal beneath its shining halo. The glowing beauty of a comet can be misleading. Beneath the bright coma, the nucleus is often extremely dark. Its surface is coated with dust and organic rich material that reflects very little sunlight. In photographs from spacecraft, comet nuclei can look rugged, blackened, and surprisingly rough, with cliffs, pits, and shadowed plains. The brilliance we see from Earth mostly comes from gas and dust surrounding the body, not from the surface itself. This creates a fascinating contrast. One of the most luminous objects in the night sky may have a heart that is almost black. It is like a lantern wrapped around charcoal. The glow is temporary, created by solar heating, while the nucleus underneath remains a dark, ancient relic. Some comets come from a shell beyond the planets, far beyond Neptune, and far beyond the familiar region of the planets. Astronomers think the solar system is surrounded by an enormous reservoir of icy bodies. This distant region is called the Oort cloud. It has never been directly seen as a whole, but the orbits of long-period comets point toward its existence. A passing star, a galactic tide, or another gravitational disturbance can nudge one of those frozen bodies inward. After that, it may fall toward the sun from an almost unimaginable distance. These comets can arrive from any direction as if dropped from the outer darkness. Their journeys remind us that the solar system is much larger than the planets suggest, with a distant frontier full of silent frozen worlds. Comets are sometimes called dirty snowballs, but that name is misleading. The phrase sounds simple, almost childish, as if a comet were just a lump of ice mixed with dust. The truth is stranger. A comet is a layered archive of frozen gases, rocky grains, carbon-rich material, minerals, and ancient chemistry preserved in extreme cold. Some parts may be fragile and powdery. Others may be tougher, crusted, or fractured by repeated visits near the sun. The ice inside is not only ordinary water ice. It can include carbon dioxide, carbon monoxide, methane, and other frozen substances that behave very differently in space. So the old nickname captures only one corner of the story. These objects are not messy snowballs drifting through emptiness. They are complicated little worlds built from the raw ingredients of planets and stored in darkness until heat reveals their hidden nature. Their icy nuclear I can be only the size of a small town. It is astonishing to think that something so small can create such a grand display. The solid core of a comet may measure only a few miles across, comparable to a town or city district on Earth. Yet that compact body holds enough volatile material to produce an enormous cloud and sweeping tails when warmed by the sun. If you could stand far above one, the landscape might look like a frozen wasteland of pits, ridges, dust, and shadow. There would be no wide horizon like a planet. It gives you only a tiny world curving away quickly beneath your feet. Its small size also means weak gravity, so loose material can escape with surprising ease. A modest nucleus becomes magnificent because it does not need to be large. It only needs sunlight, ice, and time. Sunlight turns frozen comet ice directly into gas. On Earth, ice usually melts before it becomes vapor in the near vacuum around a comet. The process can skip the liquid stage almost entirely. As sunlight warms, exposed ice molecules break free and escape straight into space. This process is called sublimation, and it is one of the main reasons comets come alive near the sun. Frozen carbon dioxide and carbon monoxide can begin escaping at colder temperatures than water. ISO activity may start while the comet is still far away. Gas rushing out from the surface carries tiny grains of dust, with it turning a dark nucleus into a visible object. It is a beautiful piece of physics. A little warmth touches ancient ice, and a body that has slept for ages begins releasing its stored breath into space. A comet's coma forms when trapped gases burst into space. The bright haze around a comet begins close to the surface, where warming ice unlocks gases that have been trapped for immense spans of time. As those gases escape, they expand outward in every direction, because there is almost no air pressure to hold them back. Dust is lifted along with them, and sunlight catches this cloud, making the comet appear soft and glowing through a telescope. The coma is not a solid shell. It is a temporary atmosphere, constantly supplied by new, escaping material, can constantly lost into space. Its shape can change as different areas of the nucleus warm, crack, or rotate into sunlight. What we see is not a still halo, but a living process. The comet is shedding itself moment by moment as ancient stores of gas stream away. Dust tails curve gently because sunlight pushes the grains behind. A dust tail is made from tiny solid particles released from the comet's surface. Once free, those grains no longer follow the nucleus perfectly. Sunlight carries momentum, and that faint pressure pushes on dust as it drifts through space. Larger grains respond more slowly, while smaller grains are swept farther and faster. The result is a broad, curved tail that can look like a pale brushstroke across the sky. This curve reveals both the comet's motion and the steady outward pressure of solar radiation. It is not random decoration. It is physics drawn on a cosmic scale. Every grain is following its own path, shaped by gravity, sunlight, and the speed at which it escaped. Together, they create one of the most graceful structures in astronomy. Iron tails glow blue as solar wind sweeps charged gas away. Some gases escaping from a comet become electrically charged when sunlight strips away electrons. Once charged, they respond strongly to the solar wind, which is the stream of particles flowing outward from the sun. This creates a narrow iron tail that often appears bluish in photographs. Unlike the broader dust tail, it tends to point more directly away from the sun, tracing the direction of the solar wind. The glow comes from molecules and ions interacting with sunlight and space particles, especially carbon monoxide ions in many comets. What makes this tail so fascinating is that it acts like a visible instrument in space. It shows the shape and movement of forces we cannot normally see, turning a comet into a natural detector of solar activity. Some comets have two tails that point in different directions. A bright comet can look as if it is unfurling more than one banner into the sky. One tail is usually made of dust, pushed outward by sunlight, and spread into a curved fan. The other is made of charged gas, swept more directly by the solar wind into a straighter line. Because dust and ions respond to different forces, the two tails can separate and point along noticeably different paths. This gives the comet a striking double form, almost like two different stories told at once. One tail speaks of solid grains released from the surface. The other speaks of charged particles, caught in the sun's invisible stream. Seeing both together is a reminder that a comet is not merely glowing, it is interacting with the whole space environment around it. A comet can briefly become visible without any telescope. Most comets remain faint, distant objects known only to observers with instruments, but occasionally one brightens enough for ordinary eyes to see. This can happen when a comet comes close to the sun, close to Earth, or releases an unusually large amount of gas and dust. Then it may appear as a soft patch in the sky, sometimes with a faint tail stretching away from it. For people who rarely look up, such a sight can feel startling. It is not a planet, not a star, and not a cloud. It is a moving visitor from the colder reaches of the solar system, briefly, bright enough to enter human experience without machinery. These appearances are special because they bring deep space into plain sight, turning the night sky into a shared event. Great comets can dominate the sky for weeks. Every so often, a comet becomes so bright and extended that it stops being only an astronomist's target and becomes part of ordinary life. People notice it after sunset or before dawn. Newspapers mention it, photographers chase it, children ask what the strange glow is. These rare visitors are sometimes called great comets, not because of their size alone, but because of the impression they leave. Their brightness depends on many factors, including distance, dust production, geometry, and how well their tails catch sunlight from Earth's viewpoint. Some become unforgettable, hanging in twilight with a visible plume that changes night by night. They remind us that the sky is not fixed scenery. It can suddenly reveal motion, depth, and history in a way that feels almost personal. Ancient people often saw comets as warnings from the heavens. Before modern astronomy, a comet's sudden arrival could be deeply unsettling. The stars seemed orderly, the moon followed its phases, the planets wandered in known patterns. Then, without warning, a strange blurred light might appear, grow a tail, and move against the familiar constellations. Many cultures connected such sights with the fate of rulers, wars, disasters, or great changes. This was not foolishness. It was a human attempt to find meaning in an unpredictable sky. Comets looked different from everything else people knew, and their timing often felt impossible to ignore. Over time, careful observation transformed fear into knowledge. Still, those older reactions tell us something important. Comets have always had emotional power long before they were understood. As I see bodies, they will remind us that the heavens could surprise us. Chinese astronomers recorded comet appearances with extraordinary care. Some of the most valuable comet records in history come from ancient China, where sky watchers treated celestial changes as matters of great importance. They noted the date, position, brightness, shape, and movement of unusual objects with impressive discipline. These records often describe comets as broom stars because of their sweeping tails. To modern scientists, such observations are more than cultural history. They can help identify earlier appearances of famous comets and reconstruct how their orbits changed over time. A note written by a court astronomer centuries ago can still matter to astronomy today. There is something wonderful about that continuity. A careful observer under an ancient sky could not know about spacecraft spectroscopy or orbital simulations. Yet their patient notes became part of a scientific chain reaching into the present. Halley's Comet helped prove comets follow predictable orbits. For centuries, comets seemed like one-time intruders. They appeared brightened, faded, and vanished into mystery. The great shift came when astronomers compared records of past appearances and realized that some might be the same object, returning on a long path around the sun. Halley's Comet became the most famous example. Its repeated visits showed that at least some comets were not random moments, but members of the solar system moving under gravity. This changed the way people understood the sky. A frightening apparition became a predictable traveler. The idea was bold because the comet disappeared for a human lifetime before returning. Yet the prediction worked when he came back. It proved that mathematics could reach far into darkness and describe the path of a body that no living observer had seen complete its journey. Isaac Newton used comet paths to test gravity itself. Comets mattered deeply to the rise of modern physics because they did not move in neat little circles. They followed stretched, sweeping paths that carried them far from the sun and then back again at great speed. Newton understood that the same gravitational law pulling an apple toward Earth could also guide worlds, moons, planets, and comets. Their motions offered a severe test. If gravity truly reached across space, then a comet's curve should be explainable by the same principles that govern the planets. This was a breathtaking unification. The heavens were no longer a separate realm with special rules. A comet crossing the sky became evidence that nature used one set of laws. From Earth's surface to the outer solar system, its path helped reveal a universe bound together by invisible attraction. Edmund Halley predicted a comet would return after his lifetime. The prediction required more than cleverness. It required confidence in records mathematics and the idea that a vanished object could still be following a hidden orbit. Edmund Halley studied earlier comet appearances and noticed that sightings from different centuries had remarkably similar paths. He argued that they were not separate comets at all, but one body returning again and again. He predicted it would come back after he was gone. That kind of claim was daring because nobody could simply wait a few nights to check it. The answer belonged to the future. When the comet returned as predicted, it became one of astronomy's great triumphs. It showed that human reasoning could outlive the reasoner reaching forward through time to greet an icy traveler on its next return. Halley's Comet last visited Earth's skies in 1986. That return was not the most spectacular one for casual observers, because the geometry was not especially favorable. Even so, it became a landmark moment in space exploration. For the first time, spacecraft from several nations was sent to study the famous comet up close. Images revealed a dark, irregular nucleus rather than the shining object many people imagined. Jets burst from active regions, spraying material into space as the comet moved near the sun. The visit linked ancient sky watching with modern engineering. A body recorded by people thousands of years earlier was finally photographed at close range by machines built on Earth. Its next return will belong to a different generation, which gives the comet a rare emotional rhythm. It is not just an object, it is an appointment across lifetimes. Mark Twain was born and died near Halley's Comet visits. Few comet stories feel as strangely poetic as the life of Mark Twain. He was born shortly after the comet's appearance in the 1830s, and he famously expected to leave with it when it returned. Remarkably, he died in 1910, just as Halley's Comet was again passing near Earth. The timing was not mystical in the scientific sense, but it is unforgettable as a human story. A writer known for wit timing and a sense of cosmic irony had his life bracketed by the same celestial visitor. It reminds us that comets are not only astronomical objects, they become woven into culture, memory, literature, and personal meaning. The long cycles make human lives feel brief, yet they also give us a way to mark time against something fast. Comet Hale-Bopp stayed visible for an unusually long time. Many bright comets are fleeting. Hale-Bopp was different. In the late 1990s, it remained visible to the naked eye for month after month, becoming one of the most widely seen comets of modern times. Part of its impact came from that unusual persistence. People could watch it return night after night, not as a quick surprise, but as a continuing presence in the sky. It had a large active nucleus and produced a tremendous amount of dust and gas, which helped keep it bright over a long stretch. For many observers, it became a shared memory of looking upward before smartphones filled every pocket. Millions simply stepped outside and saw a comet with their own eyes. Hale-Bopp turned astronomy into something public, patient, and unforgettable. Comet MC Nord became one of the brightest comets ever photographed. In 2007, this remarkable comet put on a dazzling display, especially for observers in the southern hemisphere. Its tail spread into a broad fan with delicate bands that looked almost too structured to be natural. Photographs captured it glowing after sunset with extraordinary brilliance, and for a short time, it was visible even in daylight. Under the right conditions, the beauty came from dust scattering sunlight, arranged by the combined effects of motion, radiation pressure, and viewing angle. What made MC not so memorable was not only brightness, but elegance. Its tail seemed to open like a vast celestial fan above the horizon. Such comets are rare, because many conditions must align when they do. The result is a reminder that the solar system can still produce spectacles grand enough to stop people in their tracks. Comet Neowise gave modern stargazers a rare naked eye show. In 2020, when much of the world felt unusually still, a comet appeared in the high northern sky near Wise was first detected by a space telescope designed to survey infrared light, but it soon became a gift for people on Earth. It rose before dawn at first, then became easier to see after sunset under dark skies. Observers could spot its bright head and graceful tail. Without a telescope, cameras revealed even more structure, including a separate iron tail faintly glowing beside the dust. Part of its charm was accessibility. You did not need to be an expert to find it. You only needed a clear horizon and a reason to look up. For many, Neowise became a shared moment of wonder during a difficult year, proof that the sky could still surprise us. Shoemaker Lee V9 broke apart before striking Jupiter. Before impact, Jupiter's gravity had already done something dramatic. It pulled the comet into fragments, stretching and tearing the body until it became a train of pieces moving along the same doomed path. Images before the collision showed a broken chain rather than a single object, sometimes compared to pearls on a string. This fragmentation revealed the intense tidal forces near the giant planet. A comet is not a perfect solid stone. It can be fractured, porous, and vulnerable when gravity pulls harder on one side than the other. The breakup also changed the drama of the event. Instead of one impact, Jupiter received a sequence of strikes, each fragment arriving in turn. The shattered comet became a visible lesson in how powerful planetary gravity can be. Jupiter's gravity captures and reshapes many wandering comet paths. The giant planet is more than a distant world with storms and moons. It is a gravitational gatekeeper. When comets pass near Jupiter, that paths can be bent, shortened, stretched, or completely transformed. Some are pulled into new orbits that bring them back toward the sun more often. Others are flung outward and may never return. A few are captured into families of comets that travel under Jupiter's influence like travelers, caught in the wake of a massive ship. This makes Jupiter one of the great sculptors of comet history. Its gravity does not merely attract, it edits the future. A small icy body can drift for ages on one path, then pass near the king of planets and leave on another with its destiny rewritten in a single encounter. Some comets dive dangerously close to the sun. Certain comets follow paths so extreme that they rush into the inner solar system and skim frighteningly near our star. These are the daring wanderers of comet astronomy. As they approach, solar heat becomes intense, and the surface begins to erupt with escaping gas and dust. The closer they pass, the more violent that awakening can become. Some survive the journey and swing back outward changed, but still intact. Others crack, fade, or disappear into the glare. Their paths are dramatic because they turn the sun into both a spotlight and a hazard. From Earth, we may see a brilliant flare of activity up close. The comet is being tested by heat radiation and gravity. It is a frozen relic racing through a furnace. Sun-grazing comets can vanish completely, and so are heat. For the most extreme sun skimmers, the encounter is not a close call. It is the end. As they plunge near the solar surface, their ices erupt away the dust, streams outward, and their fragile structure can break apart under overwhelming stress. Some are so small that they simply evaporate, leaving no surviving nuclears to continue the orbit. Others fragment first, creating brief streaks of brightness before fading into nothing. These disappearances are not failures of observation. They are the physical destruction of ancient bodies in real time. A comet may spend millions or billions of years preserved in cold darkness, only to be undone during one blazing passage. In that final approach, the sun becomes a great cosmic furnace, returning the comet's material to space in a last burst of light. The SOHO spacecraft has discovered thousands of sun-grazing comets. A spacecraft built to study the sun became one of history's greatest comet hunters. From its viewpoint in space, SOHO watches the region around our star where many thanked comets would be impossible to see from the ground because of daylight and glare. Its instruments block the sun's bright disk, revealing tiny objects rushing through the surrounding light. Over the years, this steady watch has uncovered thousands of small sun grazers, many belonging to related groups that may be fragments of older, larger comets. Some appear briefly and vanish. Others sweep past like sparks near a fire. The achievement is remarkable because it shows how much activity hides in places our eyes cannot search. Around the sun, small icy bodies are constantly arriving, glowing, breaking, and disappearing. Comets from the Kuiper Belt often return on shorter schedules. Beyond Neptune lies a broad region of icy bodies, and some comets that come from there settle into orbits that return on humanly imaginable timescales. These are often called short-period comets. Instead of taking thousands of years to complete one journey around the sun, they may come back in decades or less. The paths have usually been altered by the gravity of the giant planets, especially Jupiter and Neptune, until they become regular visitors to the inner solar system. That regularity makes them valuable to scientists because they can be observed again and again. Each return shows how the surface changes, how much material is lost, and how sunlight reshapes an icy body. They are not one-time wonders. They are repeat messengers from the outer neighborhoods of the planets. Long-period comets may take thousands of years to return. Some comets move on such stretched orbits that a single trip around the sun can outlast entire civilizations. They may appear once in recorded history, brighten for a few weeks or months, then vanish into darkness for thousands of years. Their paths carry them far beyond the planets before gravity slowly turns them back again. This makes each appearance feel rare and almost haunting. The people who saw one return long ago may have left only fragments of writing stone or memory. The next observers may belong to a world utterly changed. These long journeys remind us that the solar system keeps time on scales far beyond human life. A comet can visit the sun, leave, and not return until languages, nations, and landscapes have transformed. The Oort cloud may hold billions of frozen comet bodies. The outermost comet reservoir is thought to surround the solar system like a vast, distant swarm. It lies so far away that the planets would be only a tiny central region by comparison. Scientists infer its existence from the arrival directions and orbits of long-period comets. If the model is right, it contains an enormous population of icy bodies left from the formation of the solar system, scattered outward by the giant planets long ago. Most of them never come near the sun. They remain cold, dark, and almost perfectly hidden. The idea is staggering. Our solar system may be wrapped in a remote cloud of ancient objects, too faint to see individually, waiting in stillness until gravity sends a few inward. as rare bright visitors passing stars can disturb comets in the Oort cloud. The sun does not travel through the galaxy alone, in perfect isolation over immense spans of time. Other stars pass near enough for their gravity to tug gently on the outer edges of the solar system. For objects in the distant comet cloud, even a slight disturbance can matter. A tiny change in direction may send a frozen body deeper into space or inward toward the planets and the sun. Galactic tides can also play a role, slowly reshaping distant orbits through the gravity of the Milky Way itself. This means a comet's arrival may begin with a nudge from far beyond the planetary system. A star passing quietly through the sun's neighborhood can set an ancient ice world on a journey that ends in a glowing sky thousands or millions of years later. A college orbit can be changed by its own jets. Gravity is not the only force guiding a comet. When gas erupts from the surface, it escapes in jets that can push the nucleus slightly in the opposite direction. The effect is small compared with a planet's gravity, but over time, it can alter the comet's path. Because jets turn on and off, as sunlight reaches different regions, the pushing is uneven and difficult to predict perfectly. This is one reason comet orbits can require careful updating after observations. The body is not simply falling through space like a passive stone. It is leaking, thrusting, and responding to heat as it moves. Every outburst carries away material, and every escaping stream gives the nucleus a tiny shove. In this way, a comet participates in its own wandering. Comet jets act like tiny thrusters on the spinning world. Imagine a small icy body turning in space, while narrow plumes burst from crack pits or sunlit patches. Each plume releases gas and dust, and the escaping material pushes back against the surface. If the jet is off-center, it can change the spin of the nucleus, making it rotate faster, slower, or in a slightly different way. Over repeated passes near the sun, these effects can become important. A comet's day length may shift, its surface may be exposed to sunlight in new patterns, fresh areas may awaken, while old active regions fade under dust. The whole object becomes a restless machine powered by solar heat. It has no engine, no metal, and no design, yet its jets can steer and spin it like natural rocket exhaust. Some comet surfaces have cliffs taller than skyscrapers. Spacecraft images have shown that comet landscapes can be surprisingly dramatic. Instead of smooth balls of ice, they may have steep walls, fractured terraces, shadowed pits, and rugged slopes. On a small body with weak gravity, cliffs can rise to extraordinary heights relative to the world itself. They are shaped by sublimation, collapsed dust movement, and a slow weakening of material as ice escapes beneath the surface. A cliff on a comet is not like one on Earth, carved by rain or rivers. It is sculpted by sunlight and vacuum, by material disappearing rather than flowing. Standing near such a drop would feel surreal. The horizon would curve close by, the sky would be black, and the ground beneath you would be an ancient mixture of dust, ice, and fragile stone. Rosetta found towering pits on Comet 67P. When the Rosetta spacecraft studied its target up close, it revealed deep circular openings in the surface, some with steep walls and shadowed interiors. These pits look like entrances into the body's hidden structure. Scientists think some may form when buried ice supplements, leaving cavities that eventually collapse. Others may expose layers or weak zones beneath the crust. Their walls showed textures, ledges, and bright patches that hinted at fresh material. The discovery made the comet feel less like a simple lump and more like a changing landscape with internal architecture. Each pit was a clue to how heat moves through the surface, how voids develop, and how material fails under weak gravity. Rosetta turned a distant blur into a place with geography, hazards, and secrets. Phyla became the first lander to touch a comet in 2014. A small lander separated from Rosetta and descended toward a world no machine had ever reached before. The target had almost no gravity, so landing was incredibly difficult. Harpoons and anchoring systems were meant to hold the craft in place, but the touchdown did not go as planned. Even so, the moment was historic. Humanity had placed an instrument package on a comet's surface. That achievement joined imagination with engineering in a breathtaking way. A frozen body that had spent ages circling the sun was suddenly being touched by a machine built on Earth. The mission showed how far exploration had come. We were no longer only watching comets through telescopes. We were arriving at them gently, precariously, and with immense curiosity. Feeler bounced across the surface before coming to rest. The landing became even more dramatic because the little craft did not stay where it first touched down in the comet's weak gravity. It rebounded and drifted across the OC surface before settling in a shaded location. That unexpected journey made communication and power difficult since its solar panels received less light than planned. Yet the lander still returned valuable measurements before its battery faded. The bounce itself became part of the science. It revealed how strange landing on a tiny comet can be, where a gentle contact can turn into a slow-motion leap. On Earth, weight holds us firmly down. On a comet, the rules feel dreamlike. A machine can touch the ground, rise again, and travel across an alien landscape almost like a feather. Rosetta followed one comet as it awakened near the sun. Most missions catch a brief glimpse of a world. Rosetta did something rarer. It escorted its comet for many months, watching the surface change as solar heating increased. Activity began in small regions, then grew stronger as more ice warmed and more dust escaped. Jets brightened, the surrounding cloud thickened. The environment around the spacecraft became more hazardous and more scientifically rich. This long companionship allowed scientists to see a comet as a process rather than a snapshot. They watched seasons of activity unfold on a tiny world guided by sunlight and rotation. It was like observing a frozen creature stir from hibernation. The mission revealed that comet behavior is not simple or uniform. It is local, changing, textured, and deeply tied to the shape of the nucleus. Comet 67P has a shape like a rubber duck. When Rosetta's images first revealed the nucleus clearly, its outline surprised almost everyone. It had two lobes joined by a narrower neck, giving it a shape that many people compared to a bath toy. The comparison was playful, but the science was serious. Such a form affects how sunlight falls on the surface, where material escapes, how dust moves, and how gravity behaves around the body. The neck region became especially interesting because it showed intense activity and complex textures. Instead of a simple sphere, the comet was a world with uneven regions, shadows, slopes, and changing illumination. Its strange shape helped scientists understand why activity came from some places more than others. Even a comet's silhouette can influence its life near the sun. That strange shape may come from two bodies joining gently. One leading explanation for the double-lobed form is the two smaller. I see objects collided at low speed and stuck together rather than destroying each other. In the early solar system, gentle mergers may have been common among small bodies. If that is what happened, the comet preserves a record of slow construction from ancient times. The join between the lobes may be a contact region where two separate histories became one object. That possibility makes the shape more than a curiosity. It becomes evidence of how tiny worlds assembled before planets finished growing. Not all collisions are violent catastrophes. Some acquired unions slow enough to build rather than break. A comet shaped like two joined pieces may carry the memory of one of those delicate encounters. Rosetta heard a comet sing in magnetic vibrations. The phrase sounds poetic, but it refers to real measurements. Instruments around the comet detected oscillations in the magnetic environment caused by interactions between escaping gas-charged particles and the solar wind. When scientists converted those variations into audible frequencies, they produced a strange warbling sound. The comet was not singing through air, because space has no air for sound waves like ours. Instead, it was creating patterns in plasma and magnetic fields. This is what makes the discovery so captivating. A silent object moving through vacuum can still produce rhythms that instruments translate into something we can hear. It changes the way we imagine space. The solar system is not mute. It is filled with waves, pulses, and vibrations, waiting for the right tools to reveal them. Comets can release oxygen trapped since the solar system's youth. Rosetta made a surprising discovery when it detected molecular oxygen around its comet. Oxygen molecules are reactive, so scientists did not expect them to remain easily preserved for billions of years. The presence suggested that the oxygen may have been trapped in icy material very early before the comet fully formed and then stored in the deep cold. As the comet warmed, the ancient molecules escaped along with water vapor and other gases. This finding was important because it challenged assumptions about chemistry in the young solar system. It showed that some delicate compounds can survive inside comet material over enormous spans of time. A gas released near the Sun may therefore be a preserved sample of conditions from the solar system's earliest nursery. Rosetta found complex organic molecules on a comet. One of the mission's most exciting results was the detection of carbon-based compounds, more elaborate than simple gases. These molecules matter because carbon chemistry is central to life as we know it. Although finding such compounds does not mean finding life, it means comets carry some of the chemical complexity that can contribute to prebiotic environments. The discovery strengthened the idea that icy bodies help distribute organic material through the young solar system. The comet is not just frozen water and dust. It is a chemical archive containing ingredients shaped by cold space radiation and ancient formation processes. When those materials are released near the Sun, scientists get a fleeting chance to study them. In that sense, Rosetta was not only exploring a comet, it was reading chemistry from the dawn of planetary history. Comet dust can contain minerals formed near the young Sun. One of the great surprises in comet science is that these cold bodies can contain grains that were born in heat. Some minerals found in comet dust could only have formed close to the young Sun, where temperatures were fierce enough to reshape raw material. Yet comets formed far away in the colder outer regions. This means the early solar system was not neatly divided between hot inner material and frozen outer material. It was mixing. Tiny mineral grains must have traveled outward through the young disk of gas and dust before being locked into icy bodies. A comet can therefore hold both extremes at once. It carries frozen substances from the dark edges and heat-forged particles from near the newborn Sun in one handful of dust. If you could hold it, there is a map of a restless solar system taking shape. Stardust returned comet grain safely back to Earth in 2006. A capsule from the Stardust mission landed in the Utah desert with an extraordinary cargo. Inside were tiny particles collected from Comet Wild 2, captured during a high-speed flyby and brought home for laboratory study. This was one of the first times material from a comet had been returned directly to Earth. The grains were small beyond everyday imagination, yet they were scientifically precious. In laboratories, researchers could examine them with instruments too large and delicate to send on the spacecraft. Each particle offered clues about minerals chemistry and the environment where the comet formed. The mission turned a distant visitor into something humans could study under microscopes. It was as if the solar system had mailed us a few specks of its childhood. Some comet particles were caught in aerogel lighter than foam. Catching dust from a comet is harder than it sounds. The grains were moving incredibly fast, and a normal collector might have shattered or vaporized them on impact. Stardust used aerogel, an extremely light porous material, sometimes called frozen smoke. When particles struck it, they slowed, gradually leaving carrot-shaped tracks through the delicate substance. This allowed many grains to survive the encounter. The idea was beautifully clever. Instead of stopping comet dust with force, the spacecraft let it sink softly through material so airy that it was mostly empty space. Later, scientists searched those tiny tracks like detectives following tunnels through glassy mist. Each trail ended with a fragment from another world. The collector looked fragile, but it performed a remarkable task, catching pieces of a comet without destroying their story. Deep Impact blasted a crater into Comet Tempel 1 in 2005. NASA sent a heavy impactor directly into Comet Tempel 1, while the separate spacecraft watched from a safe distance. The collision was intentional. Scientists wanted to excavate material hidden beneath the surface and study what came out. When the impact struck, it released a bright plume of dust and gas, briefly hiding the exact crater from view. The experiment was bold because it treated a comet like a natural laboratory. Rather than only observing what sunlight exposed, mission created its own event and watched the response. The blast showed that the surface was more powdery and complex than many expected. It also proved that carefully planned impacts could reveal layers that ordinary flybys might miss for a moment. Humanity struck a comet not to destroy it, but to ask what lay beneath. The impact revealed fresh material hidden beneath a dark crust. The surface of a comet can become altered by sunlight radiation and repeated heating, which leaves a darker outer layer over more primitive material below. When Temple 1 was struck, the plume carried newly exposed substances into space. Instruments detected dust, ice-related material, and chemical signatures that helped scientists compare the aged surface with the interior. That difference matters. A comet's skin may be weathered by its journeys, while deeper regions can preserve older conditions. The impact acted like opening a sealed drawer in a very ancient archive. It did not uncover a simple block of clean ice. It revealed a mixture with fine particles and volatile material released together. The lesson was clear. To understand comets, scientists must look past the dark surface and search for the more protected story underneath. Comet interiors may preserve chemistry older than Earth. Deep inside a comet's sunlight has done very little work. The outer crust may change with every close approach, but buried material can remain cold and protected for immense spans of time. That makes the interior scientifically precious. It may hold chemical arrangements that formed before Earth finished growing when the solar system was still a disk of gas, dust, ice, and colliding fragments. These preserved materials can tell us what ingredients were available during planet formation. They also help reveal how complex chemistry developed before oceans, continents, or living cells existed here. A comet is not perfectly unchanged, but parts of it may be among the closest things we have to original solar system material. Studying those interiors is like listening for a faint memory from before our planet had a surface to remember anything at all. Water in some comets differs from Earth's ocean water. Scientists can compare water by measuring the balance between ordinary hydrogen and a heavier form called deuterium. This ratio acts like a chemical fingerprint in some comets. That fingerprint does not match Earth's oceans very well. The difference suggests that those particular comets could not have been the only source of our planet's water. This was important because people once imagined comets as obvious ocean deliverers. The real story is more complicated. Earth's water may have arrived from multiple sources, including icy asteroids and different families of small bodies. Comets still matter, but they are not all chemically alike. They water records where and how they formed. A mismatch is not disappointing. It is a clue telling us that the early solar system had many reservoirs, each with its own hidden history. Other comet water may resemble Earth's oceans more closely. Not every comet gives the same chemical answer. Some measurements have found water ratios closer to those in Earth's oceans, especially among certain comets linked to the outer planetary region. This opened the possibility that some icy bodies could have contributed meaningfully to Earth's water, even if others did not. The important point is variety. Comets are not a single uniform class with identical ingredients. Their compositions can differ depending on where they formed, how they migrated, and what materials were mixed into them. This makes them valuable witnesses rather than simple suspects. Each one offers a separate testimony about the solar system's early chemistry. When a comet's water resembles ours, it feels like finding a distant cousin in the dark, carrying a signature that echoes the seas of our own world. Comets may have delivered some water to early Earth. Young Earth was shaped by heat, impact, and constant change during that early era. Icy bodies struck the growing planet far more often than they do today. Some of them may have brought water trapped as ice, along with other volatile materials that are easy to lose during planet formation. Even if comets were not the main source of the oceans, they may have supplied part of the total inventory. The idea is powerful because it connects the water in waves, clouds, rivers, and bodies to objects from deep space. A drop in the sea may carry a history that includes collisions, migration, and frozen material falling inward from the outer solar system. Earth did not receive its life-supporting ingredients in one simple moment. It gathered them through a long and turbulent beginning. They may also have delivered carbon-rich molecules to young planets. Water is only one part of the comet story. These icy bodies also contain carbon-based compounds, some simple and some more complex, that could have enriched young planetary surfaces. Earlier was a place of energetic chemistry, with impacts, volcanoes, lightning, sunlight, and oceans all interacting. Deliveries from comets and similar bodies may have added extra ingredients to that laboratory. This does not mean comets brought life ready-made. It means they may have contributed pieces to the chemical environment from which life eventually emerged. The same may have happened on other worlds too, including Mars or icy moons. In that sense, comets are not only remnants, they are curious. They move material between regions of the solar system, helping scatter carbon chemistry across worlds that might later transform it in unexpected ways. A comet nucleus can rotate in just a few hours. Although a comet may spend ages traveling around the sun, its own day can be surprisingly short. Some nuclei spin once in only a handful of hours, while others rotate more slowly. That spin controls which regions receive sunlight, when jets turn on, and how heat moves across the surface. On an irregular body rotation can create strange patterns of dawn and shadow. A cliff may flash into sunlight, release gas, then fall dark again before the process changes elsewhere. Measuring rotation helps scientists understand why activity appears in certain places at certain times. It also shows that these small worlds have rhythms of their own. A comet is not just moving along in orbit, it is turning, warming, cooling, and revealing different faces to the sun as its short days pass. Some comets tumble because their jets push unevenly. Not every comet spins cleanly like a well-balanced top. Jets erupt from irregular surfaces, and those escaping streams can target the nucleus from awkward angles. Over time, this can produce a tumbling motion where the object rotates around more than one axis. Such movement makes the pattern of sunlight complicated. Regions may enter and leave warmth in shifting ways, and the timing of activity becomes harder to predict. Tumbling also reveals something intimate about a comet. Structure, its shape, weak gravity, and active spots all combined to determine how it moves. The result is a body that behaves less like a clockwork sphere and more like a lopsided relic responding to its own outbursts. Even its spin can carry the signature of hidden vents, fragile terrain and uneven. Loss of material. A comet can lose tons of material every second. When a comet becomes active near the sun, the scale of its shedding can be extraordinary. Gas escapes, dust lifts away, and streams of material spread into space. During strong activity, the loss can reach tons each second. That sounds enormous, but compared with the whole nucleus, it may still allow the comet to survive many returns. The process is both spectacular and tragic. The glow that makes a comet beautiful is produced by its own gradual disappearance. Every brightening is also erosion. Every tail is material that will not return to the surface. Over time, this loss reshapes. The body buries some regions under dust, exposes others, and weakens cliffs and layers. A comet's display is therefore not decoration. It is the visible cost of coming close to the sun. Each solar visit can slowly strip a comet away. A returning comet pays a price each time it enters the warm inner solar system. Ice escapes from the surface, and near subsurface is lifted, shifted, or left behind as a coating. Active regions can fade as their volatile material is exhausted, while cracks and collapses may expose new supplies. After many passages, the body can become less active and more depleted. Its shape may change, its spin may shift, and its surface may grow darker and more insulated. This slow stripping can take many orbits, but the direction is clear. The sun wakes a comet, and the waking consumes it. These objects are ancient, yet they are not permanent. Their beauty is temporary on cosmic timescales, created by the very process that gradually wears them down. Dead comets may become dark asteroids after losing their eyes. When a comet has lost most of the volatile material near its surface, it may no longer produce a noticeable kernel or tail. What remains can look like a dark asteroid, a quiet object moving through space without the show that once revealed its nature. Such bodies are sometimes called dormant or extinct comets, depending on whether deeper ice might still survive from a telescope. Telling them apart from asteroids can be difficult. Their orbit's darkness density or occasional weak activity may provide clues. This possibility blurs the boundary between categories. A small body may begin as an icy comet, become exhausted by repeated solar heating, and end as a nearly silent remnant. The solar system is full of such transformations, where identity changes as material is lost. Some asteroids may actually be extinct comets. Astronomers sometimes find objects that behave like asteroids, but travel on comet-like paths. Their orbits may be stretched, tilted, or influenced in ways that suggest an icy past. Others are unusually dark, which can also fit with commentary. Surfaces coated in carbon-rich material without visible gas or dust. They may be cataloged as asteroids, but their histories could be more complicated. This matters because the labels we use can hide evolution. Asteroid and comet are not always permanent identities. They are appearances shaped by composition, temperature, and time. Assumingly, dry rock may be the exhausted core of something that once glowed with a tail. Looking at such objects invites a deeper question: how many silent wanderers in near-Earth space are actually the ashes of old comets? Meteor showers often come from dust left by comets. When comets travel around the sun, they shed trails of dust along their orbits. Those trails can remain spread through space long after the comet has moved on. If Earth crosses one of them, the particles strike our atmosphere at high speed and burn as meteors. To us, they appear as streaks of light falling from a particular region of the sky. This means a meteor shower is not random sky glitter. It is an encounter with a comet's abandoned path. The parent body may be far away, but its dust still meets Earth year after year. Each streak is a tiny fragment of a larger journey, a speck released long ago and finally consumed in our air. A comet can therefore visit us indirectly, not as a bright nucleus, but as a night of falling stars. The Perseid meteors come from Comet Swift-Tuttle. Every August, Earth passes through debris left by this large periodic comet. The result is one of the most beloved meteor showers of the year. The parent comet itself returned to only after long intervals, but its dust stream is spread along the orbit, waiting for Earth to cross it annually. When those particles enter the atmosphere, they create quick, bright streaks that seem to radiate from the constellation Perseus. Many people have watched the Perseids from fields, gardens, beaches, and hillsides, often without thinking about the distant body that made them possible. Behind each flash is a connection to Swift-Tuttle's path around the sun. The shower turns comet debris into a human ritual, a yearly reminder that the planet is moving through old trails of cosmic dust. The Orionids come from debris shed by Halley's Comet. Halley's Comet is famous for its rare returns, but Earth meets its dust more often than it meets the comet itself. The Orionid meteor shower occurs when our planet passes through one of Halley's debris streams. The particles are small, but they enter the atmosphere, very quickly producing swift streaks that seem to come from the region of Orion. There is something beautifully strange about that a comet that may not appear brightly in our sky for many decades still leaves annual traces. Its body is absent, yet its old dust keeps arriving. The Orionids allow people to experience Halley's legacy without waiting for the nucleus to return. Each meteor is a tiny message from a famous traveler written in light for a fraction of a second. Earth crosses ancient comet trails many times each year. Our planet is constantly moving through space, and its orbit intersects several streams of dust left by comets and related bodies. That is why meteor showers return on a schedule. The dates are not magical, They are geometry. Earth reaches the same regions of its orbit each year, where old particles are waiting in stretched trails. Some streams are dense and produce impressive displays. Others are faint and easy to miss. Over time, planetary gravity spreads and shifts the debris, so showers can strengthen, weaken, or produce surprises. This gives the calendar a hidden astronomical layer. Certain nights are not just dates. They are crossings the Earth, carrying oceans, cities, forests, and sleeping people. Passes through the remains of ancient comet journeys and briefly turns them into light. A tiny comet grain can make a brilliant meteor. A meteor does not need a large stone to light the sky. Many bright streaks begin as grains no bigger than sand released long ago from a comet and left drifting along its orbit. When one meets Earth, it enters the atmosphere at tremendous speed. Air piles up in front of it, heat rises fiercely, and the particle begins to burn away. For a brief moment, something almost weightless becomes visible across miles of sky. That is part of the magic of meteor, watching the light consume grand and sudden. Yet the object causing it may be smaller than a seed. A tiny fragment from a comet's past can end its journey above your head, turning ancient dust into a flash that lasts only a heartbeat but feels unforgettable. Comet dust burns because it strikes our atmosphere so fast. The glow of a meteor is not simply the particle catching fire like wood in a flame. It happens because the grain enters the atmosphere at speeds far beyond anything familiar on Earth. The air cannot move aside quickly enough. It compresses heats and tears energy from the incoming particle. At the same time, atoms in the surrounding air become excited and release light. This creates the bright streak we see. The particle is usually destroyed high above the ground, far from danger, but its speed makes it spectacular. A piece of comet dust drifting silently through space becomes a burst of light because Earth runs into it at orbital velocity. The meeting is brief, but the physics is extreme. Motion alone transforms darkness into brilliance. Some comet trails are wider than the Earth itself. The comet's debris stream is not a narrow line of dust. Over time, particles spread along and around the orbit, guided by sunlight, gravity, and tiny differences in speed. The result can become a vast river of material in space. When Earth passes through such a stream, our whole planet moves through an invisible cloud of ancient grains. Some parts are denser than others, which is why meteor showers can vary from year to year. The scale is astonishing. A trail made from small particles can be wider than the world crossing it. We do not feel the passage. Oceans, mountains, cities, and forests continue as usual. Yet above us, the atmosphere catches the evidence, turning scattered comet dust into streaks of light across the night. Comets help reveal the solar wind before spacecraft measured it long before instruments flew through. Interplanetary space comet tailies gave scientists a clue that something was streaming outward from the sun. The gas tails did not behave like ordinary smoke. They pointed away from the sun with striking consistency, even when the comet was moving in another direction. This suggested that a force was pushing material outward. Later, the idea of the solar wind explained it. The sun releases a flow of charged particles that travels through the solar system, shaping comet plasma tails as it goes. Comets, therefore, acted like natural signposts. They made an invisible flow visible before humans could measure it directly. In a sense, every bright ion tail was already drawing the solar wind across the sky long before spacecraft confirmed the stream was real. A comet tail can show invisible space weather in motion. Space weather sounds distant, but it is a real environment, shaped by solar particles, magnetic fields, and bursts of energy from the sun. Comets can reveal that environment in dramatic ways. The ion tails respond quickly to changes in the solar wind, bending, rippling, narrowing, or brightening as conditions shift. When the disturbance passes, the tail can behave like a windsock in a storm. This makes Comet useful as moving probes, even when no spacecraft is nearby. They translate invisible forces into visible structure. Watching a comet's tail is not only watching material escape from an icy body, it is watching the sun's influence sweep through space. The tail becomes a moving drawing of conditions, between worlds, a luminous trace of weather that no human skin could feel directly. Solar storms can tear a comet's eye on tail away. Sometimes the sun releases powerful disturbances that race outward through the solar system. When such a surge strikes a comet, it can disrupt the magnetic connection in the plasma tail. The tail may appear to disconnect, break, or drift away, while a new one begins forming behind it. This is called a disconnection event, and it shows how dynamic comet tails really are. They are not fixed ornaments. They are constantly being rebuilt from escaping gas and shaped by the changing solar wind. The image is extraordinary. A comet can be moving calmly along its orbit when a solar storm sweeps past and rips away part of its glowing plasma structure. Then almost at once, the comet begins drawing a new tail into space. Comets can grow temporary atmospheres larger than many planets. When gas escapes from a warming comet, it spreads outward into a vast cloud around the nucleus. This cloud can become enormous, far larger than the solid body that produced it, and larger than many planetary atmospheres in width. Yet it is incredibly thin. You could pass through much of it without feeling anything like wind or pressure. Its size comes from the freedom of gas expanding into near vacuum. The nucleus keeps supplying fresh material, while sunlight and the solar wind keep carrying it away. The result is an atmosphere with no permanent boundary and no stable home. It exists only while the comet is active. A small dark core can briefly surround itself with a ghostly envelope on a planetary scale, then lose it again as conditions change. Their atmospheres disappear again when they retreat from the sun. The comet's coma is not a lasting feature. It depends on warmth. As the comet moves away from the sun's surface, activity weakens and the supply of escaping gas fades without constant renewal. The surrounding cloud thins into space dust, settles into new layers. Volatile regions become quiet and the nucleus returns to a darker, colder state. This fading can be gradual, like a lamp dimming after a long journey through sunlight. The same body that once looked broad and glowing may later become too faint for ordinary telescopes. This cycle is one of the most fascinating things about comets. Their appearance is seasonal on an orbital scale. They bloom near the sun, then close again in deepening cold, carrying whatever remains of their surface into the outer. Dark comets smell chemically strange because they release unusual gases. No astronaut would ever stand in a comet's coma and simply breathe it, but instruments can identify the gases drifting away. The mixture would be harsh and alien by human standards. It can include water vapor, carbon compounds, sulfur-bearing gases, ammonia-related molecules, and other volatile substances released from ice and dust. Some of these chemicals have sharp or unpleasant odors on Earth. Together, they paint a picture of a body that is chemically rich rather than clean and snow-like. This is another reason comets are so compelling. They are not pure ice sculptures. They are frozen chemical storehouses holding materials that formed or gathered in the early solar system. When warmed, they release a strange invisible breath, and that breath tells scientists what the comet has been carrying for billions of years. Hydrogen cyanide has been detected in some comet comas. The name sounds alarming because on Earth, hydrogen cyanide is a dangerous poison. In comet science, its presence is not a threat to us. It is a clue. This molecule contains hydrogen, carbon, and nitrogen, which makes it relevant to the broader chemistry that can lead toward more complex compounds in the thin environment around a comet. It escapes as ice warms and then becomes part of the coma's detectable gas mixture. Scientists study it because nitrogen-bearing molecules help reveal formation conditions and chemical pathways in the early solar system. The same substance that would be deadly in a room on Earth becomes in space a messenger from frozen chemistry. Its detection reminds us that comets carry ingredients, both familiar and severe, preserved in forms shaped by cold radiation and time. Methanol and formaldehyde can also drift from comet ice. Comet gases include more than water vapor and simple carbon compounds. Methanol and formaldehyde have both been detected around comets, and each adds another piece to the chemical story. These molecules can form through reactions on icy grains in cold environments, then remain trapped until solar heating releases them. Their presence suggests that chemical complexity begins before planets are fully formed in the frozen dust and ice of space. Formaldehyde is especially interesting because it can participate in reactions that build more elaborate organic substances under the right conditions. Methanol also acts as a marker of icy chemistry. A comet releasing these gases is like a laboratory slowly opening its sealed bottles. The amounts are thin and spread out, but the message is rich. Even small icy bodies can carry surprisingly diverse molecular inventories. Comet ice can include carbon dioxide and carbon monoxide. Water ice is only part of what freezes inside comets. Carbon dioxide and carbon monoxide can also be present, and they matter because they become active for different temperatures. Carbon monoxide can escape even when a comet is still very far from the sun, where water ice remains mostly quiet. Carbon dioxide can also drive activity before the comet reaches warmer regions. These ices help explain why some comets begin producing gas and dust at great distances. They also reveal the cold conditions under which comet material formed and survived on Earth. Carbon dioxide is familiar as a gas in the air and as dry ice. When frozen in comets, it can be a buried power source. As sunlight increases, these hidden ices can awaken first, starting activity from deep cold. Some comets contain ammonia-related compounds frozen since formation. Nitrogen chemistry is important because it helps scientists understand the ingredients available in the early solar system. Ammonia and related compounds can be trapped in cometary ice dust or salts, depending on the conditions where the material formed. When comets are studied up close, these substances help reveal temperature history, chemical processing, and links to the building blocks used in planetary environments. Ammonia itself is simple, but it can be involved in pathways toward more complex nitrogen-bearing molecules. This does not make a comet alive or friendly. It makes it chemically meaningful. A frozen body traveling through space may contain records of nitrogen chemistry older than Earth's surface. Every detected compound is another clue to how the raw materials of planets' atmospheres and possible prebiotic chemistry were distributed across the young solar system. Their dark crust may protect ancient ice beneath the comet. Surface can become coated with dust and altered organic material after repeated exposure to sunlight. This dark layer absorbs heat, but it can also act as a blanket, slowing the loss of deeper ice. In some places beneath the crust, older volatile material may remain sealed away, protected from direct sunlight and the harshness of space. That is why cracks, collapses, and impacts are so scientifically valuable. They can expose fresher material that has not been processed as much as the surface. The crust is therefore both a mask and a shield. It hides the interior from easy view while helping preserve some of what lies below. A comet may look exhausted and blackened outside, yet still keep ancient ice stored in its deeper shadows. Sunlight can bake comet surfaces into black organic material. Over many passages near the sun, comet surfaces are changed by heat and radiation. Ices escape, leaving behind dust and carbon-rich residues that can become extremely dark. Ultraviolet light and charged particles can alter organic compounds, helping create complex tar-like material on the surface. This process helps explain why comet nuclei reflect so little light despite producing bright comas when active. The surface is not clean white ice. It is more like a weathered crust of processed dust and carbon chemistry. This dark coating records a history of exposure. Each close approach removes some volatile material and leaves more resistant material behind. The result is a blackened exterior that can look almost burnt, even though it formed through slow space. Weathering rather than fire, a comet can crack as heat reaches buried ice. As sunlight warms, a comet, heat is not spread evenly. Some regions stay shadowed, while others warm quickly. Beneath the surface, buried ice can begin to sublimate, building pressure in pores, weak layers, or sealed pockets. The material above may fracture, shift, or collapse. Cracks can open pathways for gas to escape, creating new active areas. This makes comet surfaces unstable in a very particular way. They are not shaped by rain plate tectonics or flowing rivers. They are shaped by heat, moving into fragile mixtures of ice and dust. A quiet patch can become active when buried volatiles find a route upward. The surface may look still from far away, but inside it is responding to sunlight stress and escaping gas in ways that can change the landscape. Suddenly, jets can erupt from hidden pockets beneath the surface. Some comet outbursts may begin below the visible crust, where volatile material is warmed and trapped until pressure finds a weak spot. When that happens, gas can burst outward, dragging dust into space and forming a jet. These eruptions may last briefly or persist as sunlight continues to reach the source region. They can brighten the comet unexpectedly and reshape nearby terrain. What makes them exciting is the sense of concealed activity. A comet surface may look dark and dusty, while beneath it pockets of ice and gas wait for the right thermal trigger. Then a plume opens into space, revealing that the small world is not in Earth. It has hidden chambers, pressure changes, and sudden releases. In the low gravity of a comet, even a modest eruption can send material far from the nucleus. Comets may build strange dunes from dust in low gravity. Dunes usually make us think of wind, but comet surfaces have almost no atmosphere. Its spacecraft images suggest that dust can still gather into ripple-like forms. The explanation may involve gas escaping through or across the surface, lifting and moving grains in the comets. Weak gravity, even a thin flow from sublimating ice, can matter. When the particles weigh so little, dust can hop, slide, and settle into patterns that look strangely familiar, even though the environment is completely alien. This is one of the joys of comet landscapes. They echo Earth in shape, but not in course. A dune-like feature on a comet is not made by desert wind. It may be made by escaping vapor, weak gravity, and tiny grains responding to forces far subtle than anything a beach or desert would require. That gravity is so weak that hopping could launch you. A comet nucleus is usually small, which means its gravity is extremely gentle compared with Earth's. Standing on one would be unlike standing on any planet. A movement that feels ordinary here could have dramatic results there. A strong jump might lift you high above the surface, and on some small bodies, it could send you away completely if you exceeded escape speed. This week, gravity affects everything. Dust falls, slowly landslides behave strangely. Spacecraft have trouble anchoring. Even loose particles can drift or bounce instead of settling quickly. The surface might look like ground, but it would not hold you with familiar strength. It is a world where motion must be careful and patient, because the boundary between a hop and departure could be surprisingly thin. A person on a comet would weigh almost nothing. Your mass would not change, but your weight depends on gravity, and a comet's gravity can be thousands or millions of times weaker than Earth's. That means a human body would press down with only the faintest force. Walking would be difficult because each step relies on friction and weight. Tools, dust, and equipment would be easy to disturb. Dropped objects might fall so slowly that they seemed reluctant to land. This makes comet exploration both fascinating and treacherous. The surface is not a place for casual footsteps. It is a delicate environment where anchors, tethers, and tiny forces matter enormously. The idea also gives a striking sense of scale. A comet can fill our sky with a tail millions of miles long, yet on its surface, gravity barely holds anything down. Comet surfaces can be soft dust over hard ice. The comet ground may not behave like ground at all. Spacecraft observations suggest that some surfaces are covered by loose, fine material that can sit above stronger, icy layers underneath. This creates a world with a strange double nature. The top may be powdery, fragile, and easily shifted, while deeper material may be tougher, colder, and more compact. A lander could touch down on what looks solid and still find itself dealing with dust crust and hidden hardness all at once. This matters because surface texture controls how heat moves, how gases escape, and how easily material can be lifted into space. A comet is not a simple ball of ice. It is a layered body with fragile coverings, buried strength, and textures shaped by sunlight, cold, and time. Some comet cliffs collapse and expose fresh bright material. A comet can change its own face when steep balls weaken sections may break away and fall, revealing material that has not been darkened by long exposure. In images from spacecraft, these fresh patches can look noticeably brighter than the surrounding surface. That brightness is precious to scientists because it points toward less altered ice or dust below the crust. The collapse may happen when buried volatile material escapes, when fractures spread, or when the quasi structure becomes too weak to support itself. On Earth, cliffs fall under strong gravity, or a comet gravity is faint, but the material can be so fragile the collapse still happens. Each exposed patch is like opening a window into the interior, showing that beneath the blackened surface, older and cleaner material can still remain. Scientists have seen landslides on comet surfaces. The idea sounds almost impossible at first, because comets have such weak gravity, yet slopes can still fail. Dust chunks and fractured material can move downhill, especially when ice beneath the surface disappears or when cliffs become unstable. These movements are slow and strange compared with landslides on Earth, but they reshape the terrain all the same. A comet landscape is not frozen in place. It evolves. Ridges slump, walls shed debris, and smooth deposits collect in lower areas. Seeing these changes helps scientists understand comets as active geological worlds, even without rain rivers or plate tectonics. The geology is driven by sunlight and escaping vapor. A slope gives way, material drifts downward, and a tiny world rewrites part of its surface in silence. Comets can split apart without striking anything. A comet does not need to collide with a planet to break, some simply fracture during their journeys. Heat can build stresses inside the nucleus. Gas pressure and open cracks. Rotation can speed up until the body becomes unstable. Tidal forces during close passages near large objects can also pull weak structures apart. Because many comet nuclei are fragile mixtures of dust, ice, and voids, they may be less like solid boulders and more like delicate ancient aggregates. When they split, pieces can drift away on similar paths, sometimes brightening as newly exposed ice begins to sublimate. Such break-ups are dramatic reminders that comets are temporary structures. They may look like singular objects from Earth, but inside they can be fractured, stressed, and waiting for one more push. Some fragments return as separate comets years later. When a comet breaks apart, its pieces do not always vanish at once. Some fragments can survive and continue traveling around the Sun on related orbits. Over time, they may separate enough to be observed as distinct cometary bodies. This creates families of fragments, like echoes of a single parent object moving through space. Each piece can develop its own activity, brightness, and fate, depending on size, composition, and exposure. The result is a kind of cosmic lineage. One original body becomes several smaller wanderers, each carrying part of the same history. Astronomers can sometimes trace these relationships by comparing their paths. A comet that once appeared whole may return as multiple visitors, reminding us that small worlds can have descendant separations and endings written across many orbits. A comet's brightness can surge suddenly and unpredictably. Even experienced astronomers can be surprised by a comet. Sometimes a faint object brightens rapidly, becoming far easier to see than expected. The cause may be a sudden outburst of gas and dust, a collapsing surface feature, newly exposed ice, or a fracture that opens a fresh, active region. Because comet nuclei are regular and partly hidden by their own dust, predicting these changes is difficult. A quiet body can flare like a secret being revealed. This unpredictability is one reason comets remain so exciting. They follow gravity, but their surfaces have their own hidden dramas. A telescope may watch a dim blur night after night, then suddenly find it transformed. The comet has not changed its orbit, it has changed its output, and the sky notices. Outbursts can make faint comets visible from Earth. A comet that should be beyond ordinary sight can sometimes become visible after a sudden release of material. When gas bursts outward, it carries dust into sunlight, increasing the reflective area around the nucleus. The comet may brighten by several magnitudes, which means it can shift from a specialist target to something many observers can photograph or occasionally even glimpse under dark skies. These events can fade quickly, or they can develop into expanding shells and changing shapes around the coma. For scientists, an outburst is a chance to study freshly released material. For skywatchers, it is a reminder that comets are not predictable decorations. They are active bodies with concealed pressures and fragile surfaces. A faint wanderer can suddenly announce itself, not by moving closer, but by opening up. Interstellar comets can pass through our solar system only once. Most comets belong to the Sun, even if their orbits are extremely long. Interstellar comets are different. They arrived from beyond our solar system on paths that are not closed around the Sun. They sweep through, are warmed briefly, and then continue outward into the galaxy. There is no second visit waiting for future generations. Their speed and trajectory show that they came from another star system carrying material formed in a different planetary nursery, but makes them astonishingly valuable. For a short time, our telescopes can study an object made around another star without leaving home. Then it is gone moving back into interstellar space. Such visitors remind us that the galaxy itself exchanges fragments, and that our solar system is not sealed away from the white or dark. Borisov was the first confirmed comet from another star system. In 2019, astronomers identified a comet with a path that showed it was not bound to the Sun. Unlike the earlier interstellar visitor, or More, this object clearly developed cometary activity with gas and dust around it. Its discovery was a landmark because it gave scientists a rare chance to study comet material from somewhere else in the galaxy. Observations suggested that in some ways it resembled comets from our own solar system. That similarity was astonishing. It hinted that icy bodies may form around other stars through processes not entirely unlike those that shaped our own comet population. Yet Borisov was also a stranger traveling on the one-way path through our neighborhood. It came from another system right near our Sun, and then moved on forever. Interstellar comets carry chemistry from alien planetary nurseries. Every comet forms in a particular environment shaped by the temperature, radiation, dust, and gases around its young star. An interstellar comet therefore carries chemical evidence from a birthplace we may never see directly. When such an object passes through our solar system, its gases and dust give astronomers a sample of another system's early construction materials. This is astonishing because planets around distant stars are usually studied by their light shadows or gravitational effects. A wandering comet can bring physical chemistry from that distant context into our observational reach. It is not alien life, it is alien formation history. Molecules released from its eyes can tell us whether other planetary systems build small icy bodies with familiar ingredients, or whether their chemistry follows paths we have barely imagined. Comets may reveal how other solar systems make icy worlds. By comparing comets from our own solar system with interstellar visitors, scientists can ask a remarkable question. Are icy bodies built in similar ways around many stars, or is our solar system unusual? Comets preserve materials from cold outer regions where giant planets, dwarf planets, and icy moons can form. If interstellar comets show familiar ices and dust, it suggests common patterns in planet building. If they show unusual chemistry, that reveals diversity. Among stellar nurseries, either outcome is thrilling. These small bodies become ambassadors from the construction zones of other systems. They may help explain how water-carbon compounds and frozen gases are stored and moved around. Young stars, a comet passing through our sky, could therefore teach us not just about itself, but about worlds orbiting suns we cannot visit. The tilted orbits can arrive from almost any direction. Many planets move in nearly the same flat plane around the Sun, like dancers on the shirt floor. Long-period comets do not always obey that pattern. They can enter the inner solar system from steep angles, sometimes appearing to dive in from above or below the planetary plane. This is one clue that many come from a distant, roughly spherical reservoir rather than a flat disk. Their arrival directions make the solar system feel three-dimensional in a dramatic way. A comet can appear from a part of the sky where no planet would travel, sweep around the sun, and vanish along another tilted path. These orbits remind us that the planets show only the central architecture. Beyond them, the sun's influence extends into a much wider and more spacious domain. Some comets travel backward compared with the planets. Most planets orbit the sun in the same direction inherited from the rotating disk that formed the solar system. Some comets, however, move the opposite way. This is called retrograde motion, and it often appears in comets with highly tilted or long-period orbits. A backward-moving comet can cross the region of the planets at very high rate of speed because it is traveling against the general flow. Such paths tell scientists that comet reservoirs are dynamically stirred and ancient. They are not orderly traffic lanes. They are archives of gravitational scattering, distant nudges, and long-term orbital evolution. A retrograde comet feels like a travel entering a city by walking against every road. It belongs to the same solar system, yet its motion reveals a wilder history. Comet names often honor people or spacecraft that discover them. A comet's name is usually a record of discovery. Some are named after the astronomers who first identified them. Others carry the names of survey programs or spacecraft that found them. This is why comet names can sound like a mixture of human history and scientific machinery. Hale-Bopp honors two observers. Neowise honors the space telescope that detected it. Shoemaker-Lee V9 reflects the discoverers and the fact that it was the 9th periodic comet they found. Together, naming turns a distant icy body into part of our story. It links careful watching, patient comparison, and sometimes lucky timing with an object that may have traveled for ages unseen behind. Many comet names is a moment when someone noticed that the faint patch of light was moving differently from the stars. Robotic surveys now find most new comets before humans notice. A modern sky is watched by automated systems that scan large areas night after night. These surveys compare images, searching for objects that shift position, brighten, or appear unexpectedly. As a result, many comets were discovered first by robotic telescopes and data pipelines rather than by someone looking through an eyepiece. This has changed comet hunting. It is now faster, broader, and more systematic. The sky contains too much motion for human eyes alone to track efficiently. Machines help find faint visitors early, sometimes while they are still far from the sun. Yet human judgment remains important because discoveries must be confirmed, measured, and understood. The romance has not vanished, it has changed form. We now meet many comets through a partnership between patient instruments and curious minds. Many comets are discovered while searching for dangerous asteroids. Planetary defense surveys are designed to find near-Earth objects that might pose future risks. While doing that work, they also discover comets. Both asteroids and comets move against the background stars, so the same careful sky scanning can reveal either one. This overlap is useful. A survey built to protect Earth also expands our knowledge of small bodies across the solar system. Some discoveries are harmless distant comets. Others may be objects with unusual bits that deserve attention. The process shows how curiosity and caution can work together. By watching the sky for practical reasons, we also uncover beauty, history, and chemistry. A faint moving dot in survey data might be checked for safety and recognized as an icy visitor. Beginning its long brightening journey, a bright comet can still surprise the whole planet. Despite all our telescopes and surveys, comets remain capable of public wonder. A newcomer can brighten more than expected, survive a risky solar passage, or develop a striking tail at just the right angle for Earth. When that happens, people far beyond astronomy begin to notice. Photographs spread, friends tell each other where to look. For a few nights, the sky feels more alive. This power comes from the combination of rarity and unpredictability. Eclipses follow precise schedules, and planets return to familiar positions, but comets can still feel like sudden visitors. They remind us that the solar system is not a completed museum. It is active, changing, and full of objects whose behavior can exceed predictions. A bright comet makes the ancient sky feel newly awake. No known comet is currently on course to strike Earth. Comets can be dramatic, but known objects are carefully tracked. Astronomers measure positions over time, calculate orbits, and refine predictions as new data arrives. At present, no known comet is on a confirmed collision course with Earth. That is reassuring, but it does not make monitoring unnecessary. Comets can come from distant regions, and long-period objects may be discovered only when they are already moving inward. This is why sky surveys matter. They improve warning time, sharpen orbital knowledge, and help scientists understand small body populations. The goal is not fear, it is awareness. Earth lives in a solar system with moving debris, and knowledge is our best tool. The more carefully we watch, the better we understand which visitors are harmless wonders and which objects deserve attention. Studying comets helps scientists understand planetary beginnings. Planets are complicated because they have been changed by heat geology, atmospheres, oceans impacts, and time. Comets are smaller and colder, so some of their material can remain closer to the early ingredients from which planets grew. By studying their dust, ice, gases, and orbits, scientists reconstruct the conditions of the young solar system. They can ask where different materials formed, how far they traveled, and how water and carbon compounds reached developing worlds. Comets are therefore not side characters in astronomy, they are witnesses. They preserve pieces of the construction process that built planets' moons and perhaps the environments needed for life. Each mission telescope observation and returned grain adds a little more to the story of how our cosmic neighborhood assembled itself. From scattered material around the young star, every comet is a frozen archive from cosmic childhood. To look at a comet is to look at a remnant of beginnings. Its ices, dust, minerals, and dark crust all carry traces of processes that started before Earth became the world we know. Some comets have been altered by sunlight. Many times others are newcomers exposing material that has spent ages in deep cold. Each one is imperfect, fragile, and temporary, yet each preserves something precious. They tell of a time when planets were still growing, when small bodies collided and scattered, and when the sun was surrounded by the raw material of future worlds. That is why comets inspire both science and wonder. They are not merely beautiful visitors. They are messages from the solar system's earliest chapter, arriving in light, dust, and vapor before fading back into darkness. And so our journey through the world of comets comes to a close. Tonight we followed these ancient wanderers from the frozen edges of the solar system to the warmth of the sun. We saw how tiny dark nuclei can bloom into glowing clouds larger than planets, how tails stretch across millions of miles, and how dust left behind can fall through Earth's atmosphere as bright, fleeting meteors. We drifted past Halley, Hale, Bob, Neo, Wise, and the shattered pieces of Shoemaker, leaving 9. We touched the strange surface of Comet 67P with Rosetta and Phyla and Gloats. The chemistry hidden inside these frozen archives, water-carbon compounds, ancient dust, and fragile gases, all carried through darkness for billions of years. And now, as those icy travelers fade back into the distance, you can let your thoughts fade with them. Let your shoulders soften. Let your breathing slow. Imagine a comet far beyond the planet, resting again in cold starlight, silent and weightless. There is nowhere you need to go, nothing. You need to hold on to just the calm rhythm of the night and the soft dark above. If you enjoyed this gentle journey, you're welcome to like, subscribe, or leave a thought below. It helps other sleepy souls find their way here too. And if you're still awake, there should be another video waiting on the screen, ready to carry you a little farther. But for now, let the comets drift away. Let the sky grow. Still let your mind settle. Sleep well and good night.